Inferential statistics. Inferential statistics involves collecting and analyzing information from samples in order to draw conclusions or inferences about a larger population. And inferential statistics involves hypothesis. A hypothesis is a logical supposition or an educated or a reasonable guess. And we want to answer the hypothesis once it's been set up. And hypothesis for research provides directions for the research as well as the framework. There are two types of hypotheses, directional and non-directional. Directional hypothesis suggests a direction, whether we're talking about a relationship or difference. So in the case of a relationship, a directional hypothesis would assert that the hypothesis is either positive or negative. In the case of the difference of means, directional would suggest that one is greater than or less than, using the symbols, the greater than and the less than. For example, here's an example of a directional hypothesis. There is a positive relationship between achievement and attendance for the elementary school children. So positive is the direction that this suggests. Right? So therefore, this becomes a directional hypothesis. There's another type of hypothesis called a non-directional, and this suggests that there is no direction to your hypothesis. So using the same example then, a non-directional hypothesis would say that there is a relationship between achievement and attendance for elementary school children. Notice that there is no positive or negative suggested here in the statement. And in setting up the hypothesis, we would use the symbols equal or equal not signs. Because there's a bit of a redundancy to do both, because once we know that in a non-directional hypothesis that there is a relationship, then by just looking at the numbers, we know if it's positive or negative. So there is that overlap or redundancy to do both. And so for the remainder of this discussion, we're going to only focus on the non-directional hypothesis. When we're doing a hypothesis testing, we always start out with a null hypothesis. Null hypothesis suggests that there is nothing or no relationship or no difference, right? And the symbol we use is HO for hypothesis null, right? For example, even if we know that there is a relationship between achievement and attendance for elementary school children, a null hypothesis would say that there is no relationship, right? Because a null hypothesis has to state that there is really nothing there. So it would say there is no relationship between achievement and attendance. And when we're doing hypothesis testing, we set up this null hypothesis and we try to prove that wrong or try to find ways to reject that null hypothesis in favor of finding there to be something or a relationship or a difference. And that's stated by the alternative hypothesis. So the alternative hypothesis is opposite to the null hypothesis. We use the symbols H1 or H2 or and so on for multiple alternative hypotheses, but for the purpose of this discussion, there's going to be one alternative hypothesis. So we're going to use the symbol HA, right? Hypothesis alternative. So keep in mind that the alternative hypothesis is a direct opposite to the null hypothesis. And as a researcher, you want to be able to reject the null hypothesis in favor of the alternative hypothesis so that you are able to make a conclusion to the effect of there being a relationship or that there being a difference between two things that you are comparing. So let's do hypothesis testing. So the key question here is, are two means alike? So we're comparing two means. And the two means we're going to compare are the sample mean and the population mean. And we choose to do either a z-test or a t-test to compare these two means. Here's a question: do my pills work? IQ pills, right? So let's assume that with my spare time, I like to work with chemistry and put some chemicals together to enhance or increase one's IQ level, right? So we know that in the population, the mean or the population mean or the true mean is 100, the standard deviation of 15. So that's known information. We've known this throughout many tests, many IQ tests that have been done. And so notice the mu and the sigma that I use to indicate that this is information about the population. So here's information about the sample. Let's say that I was able to collect 100 brave souls to be able to be in my study and take my IQ pills to be tested to see if the pills work. So after a duration of time of taking this IQ pill, let's say that my sample mean came out to be 105. So we know that the population mean is 100. They were at 100 before they took the pills. Now after the pills, their sample mean came out to be 105. So the question is, did that increase of 5 points in IQ attributable to the IQ pills, or did it happen by chance? That we can assume that, yeah, there's a little bit of an increase, but it's not significant enough for me to be able to label on the bottle to say that it significantly increases their IQ pills. So the question here to be tested is there a difference between the population mean and sample mean? The population mean being 100 and the sample mean from 100 brave souls in my study of 105. Essentially, the question is there a statistical difference between 100 and 105? So here's what we want to set up for HO and HA. HO, if you remember, is the symbol for null hypothesis. And it would state that if you were to take one mean away from the other, the difference would be 0. Right? So M1 minus M2 equals 0. Or to say the two means, 100 and 105, are assumed to be the same, not statistically different. And the alternative hypothesis with the symbol HA would say the exact opposite, right? So if you were to take one mean away from the other, there is a difference. The difference is not 0. Or to say that 100 is statistically different from 105. So we set up the HO and HA. And again, when we're doing hypothesis testing, either using a z-test or a t-test, we're going to try to reject the null hypothesis so that we can be in favor of the alternative hypothesis. So now the question of z-test and t-test, how do you decide? So here are the formulas, and if you look at it carefully, the difference between the z-obtained and the t-obtained formulas comes down to the standard deviation of the population and the standard deviation of the estimated population. So if the standard deviation of the population, the sigma, right, the little circle with the tail, if the standard deviation of the population is known to us, then it says to use the z-test, and that's because we can plug in all the numbers to calculate for z-obtained. But in the case that the standard deviation of the population is not known to us, then we have to estimate it. And we're going to estimate it using the calculation for a computational formula of the standard deviation of the estimated population, right? So that's going to be the sum of x squared minus the sum of x, right? We know this formula, all divided by n minus 1. Of course, this whole thing is square rooted. Okay, so we know that this is the formula for computational formula for the estimated population, right, for the standard deviation. So we would use this calculation, use this formula to do the calculation for this little s, right, which is the standard deviation of the estimated population. So we're basically estimating the standard deviation of the population, right? So if that's the case, then what we're calculating becomes your t obtained. So now we are doing a t-test when we have an estimated standard deviation. In the case of the example of the IQ pills, we would do a z-test because the standard deviation of the population is known. Here's that information, right? So here's the population information, the sample information. Let's do a calculation now for the z obtained. Plugging in all the numbers, the x bar is 105. minus the mean of 100 divided by the standard deviation of the population over the square root of 100 brave souls. Right? So the calculation comes out to be 3.33. So now the question is, what does that mean? We ultimately want to be able to either reject or retain the null hypothesis, right? Because this is a hypothesis testing. So once we have a z obtained, then we're ready to put it on a scale, right? So here's a scale. A scale is such that you have a normal distribution, and notice the region marked by plus or minus 1.96, and that's not an arbitrary number. And in any science, we assume there's some level of error, right? And the error is marked by this little Greek letter alpha. And the normal level of error that we expect in any research is 5% error, or 0.05. And we say that we make our decision to accept or reject a null at the alpha level of 0.05, which means that there's 5% chance of error. And that's the most common level of error that we expect. All right, so when alpha is 0.05, the z crit, or the critical value of z, is 1.96 on either side, and that's where 1.96 comes from. But here's why this is a good scale. If your z obtained, the one we just calculated, falls within these points, plus or minus 1.96, which is what we called an acceptance region, we accept the null hypothesis, and we say that the null hypothesis is true. If our z obtained falls outside plus 1.96 or negative 1.96, these tails, which we call the rejection region or the critical region, then we're going to simply reject the null hypothesis. Notice that we're always talking about the null hypothesis, right? Because that's what we're testing, the null hypothesis. We never test the alternative hypothesis because we know what to do with the alternative hypothesis once we know to either accept or reject a null hypothesis, because they are exact opposite statements. Now, there are different levels of error that we can choose from. So the most common one, and how this scale is created, is using the alpha of 0.05. So it says at the bottom, when you use alpha of 0.05, that gives you 95% level of confidence with your decision, right? And it says to use plus or minus 1.96 to separate the acceptance region from the rejection regions. But if our z obtained is large enough and we could reject the null hypothesis quite easily, then we can kind of push the envelope a little bit and use alpha of 0.01 to see if we can still reject a null, right? Because ultimately we want to be able to reject a null hypothesis, right? So with alpha of 0.01, then that gives us 99% of level of confidence. But that also means that the rejection regions become smaller. So we're using plus or minus 2.575. Okay, so instead of 1.96, we would be using that number. Okay, so that increases the acceptance region and makes the rejection region much more stringent, right? So this of the three would be the most robust level of alpha, right? And then if at 0.05, which would be a good starting point, you're not able to reject a null, then you can try an alpha level of 0.1, which is more lenient, right? That gives you a 90% level of confidence, which means you have 10% chance of error. But that's still acceptable if you can reject the null hypothesis at that level. So then the cutoff for the alpha of 0.1 would be plus or minus 1.645, which makes the acceptance region smaller and the rejection region much more wide. But that gives you 10% chance of error. But we always start out with 0.05 as the beginning point and decide whether you want to become much more stringent or lenient based on your z obtained. So let's start with 0.05. So here is the z crit, or the scale. And we notice that 3.33, our z obtained, falls in the rejection region. But I also noticed that 3.33 is by far a very large number compared to the cutoff of 1.96. So I might try using the alpha of 0.01, right, which gives you the cutoff of 2.575, and you notice that our z obtained is larger than even that, and so we would still be able to reject a null at 0.01. So then going back to the question of, is there a difference between the population mean and the sample mean? Or is there a statistical difference between 100 and 105? We could say something like this as the conclusion. The z obtained of 3.33 falls in the critical region or the rejection region with the z crit of 1.96, and we would in parentheses indicate the alpha level, right? Alpha of 0.05. And we would then conclude, therefore, the result indicates a significant difference between the population mean and the sample mean of IQ test scores. And we would say, everyday term, the pills do work. But we also know that we can afford the alpha of 0.01, so it's already underlined. So we're using the z-crit then of 2.575, and in parentheses indicate that that's for the alpha of 0.01. Same result, but we can provide these numbers, right, underlined, to show that this is a pretty strong statement, right? This states that there's really less than 1% chance of error with our conclusion. So we would say that this statement is a better statement and a stronger statement for our research. In the case that our z obtained falls in the acceptance region, this is what a conclusion would look like. Z obtained falls in the acceptance region, therefore the result indicates no significant difference between the population mean and the sample mean of IQ test scores. Pills do not work. Right? That would be our ultimate conclusion, which would mean that I have to go back to the chemicals and reconfigure to see if I can come up with better pills. So here is a summary of step-by-step way of conducting a z-test or a t-test. Although we haven't talked about the t-test yet, it's very similar and it follows the same 9 steps. So the first thing we want to do in a hypothesis testing, as you have seen before, is to state the null and the alternative hypothesis, right? So you want to state the HO, right, and then the HA. And then it says to obtain whether to carry out a one-tailed test or a two-tailed test. We know that in an earlier discussion about the directional and the non-directional, we decided that we would go with the non-directional hypothesis. And you also notice that when we set up the HO and HA, we used equal and equal not signs. So a non-directional test is, by default, the two-tailed test. So we're not interested in any direction or a one-tailed test. We're interested in establishing whether two numbers are statistically the same or statistically different. So the answer to step 2 would be a two-tailed test, right? And then in step 3 says to select a significance level alpha. We always start out with 0.05, right, as a good starting point. And then if we can afford it, if our t obtained or z obtained is large enough, then we can try a more stringent alpha of 0.01, or if our t obtained or z obtained is not very strong and you still want to try to reject a null, then we can try the more lenient one of alpha of 0.1. So for now, alpha of 0.05 would be a good starting point unless otherwise indicated in the question. Then we want to go to step 4 to decide whether to do a t-test or a z-test. And we know that that depends on whether we have this information, right? That little circle with the tail at the top, that is the standard deviation of the population. Okay? So if we know that information, we can do the z-test. But if we don't, we have to estimate and do the t-test. And then whether we do a t-test or z-test, we would then create a scale. Okay, so we kind of walked through the z-crit scale where we talked about the 3 levels of alpha and the cutoffs for the acceptance region and the rejection region. T-crit works very much the same way, except we have a little more options there, as we'll see in a minute. So whether if you're doing a t-test, you would produce a t-crit for the scale. If you're doing a z-test, then we would create a z-crit for the scale. And then number 6 is to calculate. So we're going to whether you're doing a t-test or z-test, we would do the calculation. And then step 7, 8, 9 have to do with now the results and conclusions. So in step 7, it says determine whether the observed value of the test statistic falls in the critical region. So where does it fall? Does our T obtained or Z obtained fall in the acceptance region or the rejection region? And based on that, in step 8, we're going to accept or reject a null hypothesis. And then finally, in step 9, we're going to state our conclusion, such as the pills don't work. So let's walk through the t-test now. It's very similar. And so I'm using the same numbers here, except notice that the symbol here was changed out to S. And we know that S stands for the standard deviation of the estimated population. Okay? So once we have just that information and not the actual population standard deviation, we're going to resort to doing a t-test and calculate for t obtained. So we're using the same numbers here so that it just is easier for you to follow. So our t obtained now is 3.33. So what do we do with that number? Similar to what we did with the z-test, where we then put it on a scale called z-crit, we're going to do the same thing, put it on a scale for z-crit. But in order to find the z-crit, or the critical number to cut off the acceptance region from the rejection region, we have a little bit of work to do, because this t-crit table has many options for you to decide what is the right t-crit for your test. So let's become familiar with this t-crit table. First of all, in the first column, it says the degrees of freedom, right? Degrees of freedom is really n minus 1. Right? So whatever our n is, we subtract 1, and that becomes our degree of freedom. So we know that with the IQ test pills, there were 100 brave souls, right? So the degrees of freedom then would be n minus 1, or 99. So we look for 99 in the first column, and you notice that 99 does not exist, right? So we are down to either 60 or 120. We would choose the smaller number, 60, because we have 60 cases, more than 60 cases, right? But we have at least 60. We can't select 120 because we only have 100 brave souls, right? 120 would not be the correct number. So we're going to go conservative, right? And use a smaller degrees of freedom to read off our t-crit. So we're down to now this row here where the degrees of freedom is 60. So that's a lot of narrowing down to about 5 possibilities here. Now to select the column is labeled by these little numbers here, right? And it says it's the amount of alpha in one tail, right? So which means that we need to really double up these numbers to know our alpha. So our alpha here for 0.1 would be 0.2 because it's double that. And this would be 0.10. And then this would be, I'm just doubling up the numbers, 0.05 and 0.02. And this would be 0.01, right? So those would be your alphas. But we also know that, as we have talked about in the z-crit, we're using just 3 alphas because those are the most commonly used ones, 0.05, and then the more stringent one of 0.01, and the most lenient one of 0.1. So that's what we're going to stick to and select only those columns that are indicated by these alphas, right? So that means we're not going to use this column and this column. So that eliminated the 2 columns and gave us the 3 possibilities now. So at the alpha of 0.1, we have a t-crit of 1.671, at the alpha of 0.05, 2.0, and at the alpha of 0.01, 2.660. Okay? So let's start out with 0.05, right? This column. And I have boxed in here the t-crit of 2.000. So that's a good number to use to set up the acceptance region from the rejection region. So here's the scale with the t-crit of plus or minus 2.00. So now we know the acceptance and the rejection regions have been separated by that number. Our t obtained, if you remember, was 3.33, and it falls in the rejection region and is much higher than 2.00. Very nice number, right? So we know that we want to reject the null hypothesis at the 0.05 level. Okay? Can we reject the null at the 0.01 level? If you go back to the table here, we know that at 0.01 level, the t-crit is 2.660. And we could still reject a null if we move the 2.00 out to 2.660 and still be able to reject a null. All right, so to answer the question then, to this question, is there a difference between the population mean and the sample mean? This is what we would report. The result indicates a significant difference between the population mean and the sample mean of IQ test scores. And notice these symbols that we use to kind of summarize what we did. So in brackets, then we see T to indicate that we did a t-test. And any guesses on what 99 is? That's the degree of freedom, right? Because we know that there were 100 people, and n-1 of 99 is your degrees of freedom. So 3.33 is your T obtained, right? So that's reported. And we also know that 0.01 over here is your alpha, right? Because we indicated that that's the alpha level that we choose, right? Because we could still reject a null at that point. But notice here, P less than, right? So P less than is used to show that our T obtained was significant, right? That it was in the rejection region at the 0.01 level. So when we're reporting a significant difference, we use the symbol P less than. If we're reporting a not significant difference, then we would use P greater than, right? This is for not significant. But in this case, we know that our T obtained was a nice big number and clearly in the rejection region. So we're going to use the symbol P less than to indicate that there was a significant difference.